These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, let's try this.
So you have a point source, and it's generating 100 watts. And you want to know the intensity, and the intensity is power over area. And it's a point source, so it'll generate like a circle, I think. And you're told you want it 5 meters. So the area would be pi times 25. So your intensity.
Okay, so it's good that you partly. So it's good that you drew a picture. Here's the point source. And something that you did that was important is you figured out. Maybe I should have said what type of power or energy this is. So we can say, well, it doesn't matter that much. It's some types of power or energy that's emerging in a kind of a wavefront. So you said the wavefront was a circle.
Yeah.
However, in real life, a point source would not actually emit a circle. It emits a slightly different geometric shape.
Okay.
Any idea what I mean?
No.
Since it exists in 3D, it would emit a spherical wavefront. Because there's no reason, if it's a point, there's no reason to prefer only emitting in the board. It's also going to front and back. Okay. So you're on the right track with the circle, but that's not quite symmetrical enough. We need a spherical wavefront.
Okay.
How does that change things for us?
So then it's a sphere. So
Yeah, that's hard to draw, but we can at least think of it. Good.
So your area is not going to be that.
Good.
Oh no.
I would control Z that.
Okay. So your area is going to be 4 pi r squared?
Great, good.
The surface area of the sphere.
That's good, you know that.
So it's 4 pi times 25. So 100 pi. So your intensity would be 100 divided by 100 pi. 1 over pi.
That's good enough. Good. So let's put in the units for that.
Yeah. Watts per meter squared.
Okay, excellent. Good. You might be wondering if there's a name for that unit, but I don't know of one. So those are good units, watts per meter squared. Good. Okay. All right, so you partly remembered how to do this, and then there was also a problem. So you saw that you had to, it's good that you tried to see what the wavefront would be. However, if it's really a point source, it should emit in all directions in 3 dimensions, which would be a sphere. Why did I say it was a point source? Because that's the clue that it's a spherical wavefront. Other types of sources might emit a different type of wavefront, but a point source is going to be a completely symmetrical wavefront. So you use this important equation. Intensity is power over area. So this is a good equation. And one thing we saw here is different problems will involve different areas. So when you make your cheat sheet for the test, you're going to want to put in the formula for an area of a sphere, although you already knew that. So that was 4 pi r squared. Good. We don't confuse that with the area of the circle. Okay, good. I didn't tell you this was a power, but because you have the units memorized, you figured it out. Good. Let me add this. Okay, good. See, I got a little bit ahead of myself there. So, what is light?
Light is a wave.
That's a good start. That's a lot more than people knew for a long time. That's right. Light is a wave. That's a good answer. But in a wave, something has to be waving. For example, a water wave, the water molecules are waving. Or in a sound wave, the air molecules are waving. Or in a string wave, the string is waving. Or, let's be more concrete, something has to be oscillating in a wave. So in the water wave, the water is oscillating, or in a sound wave, the air molecules are oscillating. What is it that's oscillating in a light wave?
Is it the electric fields and the magnetic fields?
That's an excellent answer. Excellent. Very good. Very good. Very good. So yeah, that is what light is. So what is light? Light is oscillating electric and magnetic fields. That's a good answer. Notice that that makes it more complicated than other waves because there's two things oscillating simultaneously, unlike the other examples I gave you. All right, well that might not seem very impressive, but think about how mysterious light was for so long. You know, for thousands of years, people must have thought it was impossible to do science on light. You know, you can't measure it, you can't put it in a bucket. It seemed like it would almost be impossible to investigate it, but actually we've been able to figure out actually what light is. It's these oscillating electric and magnetic fields. So you can see why we're talking about this now, because we've just hopefully learned a lot of the details about electric and magnetic fields. So now we can apply that to light. Now, unfortunately, it turns out that even though that's a nice answer, light turns out to be more complicated than that, because we're going to see in a couple of weeks that unfortunately, even though sometimes light acts as if it were a wave, sometimes it acts as if it were a particle. So actually all we can say is that we're using a model. We can model light as oscillating electric and magnetic fields as a wave for some problems. But there's other problems we'll study later where we have to model it as a particle. But at least in one perspective it is a wave. Okay, so let's see. So let's see how that works. We've seen that what happens when you have a changing magnetic flux? What does that create?
An induced current.
That's right. An induced voltage and an induced current. Well, something we haven't quite talked about. You had a couple of homework questions about this. We haven't quite talked about it. That's not the fundamental thing that the changing flux creates. The fundamental thing the changing flux creates is an electric field. The changing magnetic flux creates the electric field. And that's what causes the current. So we haven't really, this usually isn't tested directly, but this is one thing that it's causing. Now, we haven't talked about this. You studied, what's this the symbol for?
Electric flux.
Electric flux. You and I haven't worked on that, but you studied that for Gauss's law. Electric flux is important for Gauss's law. We haven't discussed this, but changing electric flux also causes something. Changing electric flux also causes something. You didn't study this for Gauss's law. This is just in the latest chapter. This is something I think that Maxwell figured out just by symmetry. He said, well, if changing magnetic flux causes an electric field, what would be the symmetrical thing for the changing electric flux to cause?
Changing B field?
Yeah, it would cause a magnetic field. I think he first predicted that just because he thought it would be cool to have the symmetry. But then people went out and did experiments and they found out that it actually works that way. So we haven't actually done any problems like this, but this is new material from the new chapter. Well, now we can see how an electromagnetic wave works, because it has an oscillating electric field, which causes a changing electric flux, which causes the magnetic field. And the magnetic field is also changing, which causes the changing magnetic flux, which causes the electric field. And that's also changing, which brings us back to here. So it's a self-reinforcing process where the changing electric field keeps causing the magnetic field, and the changing magnetic field keeps causing the electric field. Now, this is something that's new that we've never seen before. We've done problems with electric fields, and we've done problems with magnetic fields. We even did a couple problems with both an electric field and a magnetic field. Remember, we did the problem about making something move in a straight line? but how to have the electric and magnetic fields cancel each other. But we never did something where the electric and magnetic fields were causing each other. So this is something new. We've never studied these electromagnetic waves before because we never did the problem. The problem we did before, they were separate electric and magnetic fields, but these are tied together because they're causing each other. Okay, so now we know a little bit more clearly what light is. You said earlier that light is oscillating electric and magnetic fields, but we didn't explain why would they be oscillating. Well, it's a self-reinforcing process where each of them is causing the other one to occur. Do you know whether sound can travel through a vacuum?
It cannot.
It cannot. Why would it not make sense for sound to travel through a vacuum?
Because it needs like matter to propagate off of.
Yeah, it needs matter. Sound is usually like air, but there's no air in space, so there can't be any sound. That's right. Can light travel through a vacuum? Mm-hmm. But if it's a wave, how can it travel through a vacuum if there's nothing to oscillate? So your answer was correct. Mm-hmm. What is it that's oscillating in the electromagnetic wave? What is it that's oscillating? This is something we already talked about.
Oh, we did.
This is something you told me. What is it that's oscillating in an electromagnetic wave?
The electromagnetic wave? I said this?
It's the electric and magnetic fields.
Oh, okay.
Right?
Yeah.
When I asked you what light was, you said oscillating electric and magnetic fields. Okay, so that's correct. So these are the things that are oscillating. Well, the key thing is, can there be an electric field in a vacuum? Is an electric field a property of space or a property of an object?
Space.
Yeah, I guess maybe you and I haven't quite talked about this, but I think I might talk about it in some of the videos. Forces have to be exerted on objects. If there's no object, there can't be a force. But fields are just properties of space. What we're imagining is that charges and currents alter the space around them. It's kind of mystical. It's hard to say how can you alter the space, but in some way they're altering the space by creating these fields. So fields can exist in a vacuum. The fields can exist in a vacuum, and that explains why light can travel through a vacuum and sound can't. The light is something that's oscillating that just changes in the space. All right, this is the reason why the sun can warm up the Earth, because the light rays have to be able to travel through the vacuum from the sun to the Earth. Okay. One reason I'm going over this is I think it gives some useful background. But this is a chapter where their instructors are a little more likely to ask a little bit more type essay or thought or historical type questions. So it's good to know a little bit of the conceptual and historical background here, because sometimes they don't just ask calculation questions. Sometimes they ask about some of these things we've been talking about. Okay. So now we know what light is. Something that I've noticed sometimes is tested on the exams is, so where does the light come from originally? So I hope that I've explained to you how the light can propagate itself once it exists, but where did it come from in the first place? And the answer is there must be something originally that caused these changes. So there's a very short, simple answer. Electromagnetic waves come from accelerating charges. They come from accelerating charges. And this is something I definitely have seen sometimes tested directly on exams. So this is a good phrase to have in your pocket. Where does light come from? It comes from accelerating charges. For example, it might come, say, from oscillating electrons that are moving back and forth. Although it could be any type of acceleration. If an electron is moving in a circle, that's also acceleration because its direction is changing. So if the charge is accelerating or oscillating, that's going to, charges create electric fields, and moving charges create magnetic fields. And if it's moving around, it's going to create a changing electric and magnetic field. That's how the electromagnetic wave gets started, and then it's self-reinforcing. It just propagates itself through space. So now we see where the light started, and then how it can propagate itself through space. One thing we haven't talked about is that electric and magnetic fields store energy. You and I haven't worked on that, but there's been some problems in the homework about how much energy is stored in electric and magnetic fields. This is why light carries energy. So when the light moves from the sun to the earth, the energy from the sun is being carried by these electric and magnetic fields, and then when it hits the earth, it's delivering energy to the earth from those electric and magnetic fields. For example, remember we just did a problem about an inductor, and we saw how the inductor had a bunch of energy stored up so that it could act like a battery. The energy is stored up in the magnetic field inside the inductor. And then when it gets to the earth, we can do problems like this. So the electromagnetic waves are carrying energy and power, and we can try to figure out, so this might, for example, might be a light bulb, a 100-watt light bulb, and you might, it's generating electromagnetic waves that move away from the light bulb, and we might want to know what's the intensity that we get 5 meters away from the light bulb. So, so usually these concepts of power and intensity are being tested here for these electromagnetic waves. Okay, good. Let's make a little flow chart. What would be a good symbol for power?
P.
Good. Although maybe I won't write that down. Maybe we should avoid that right here because there's also some problems in the homework about pressure, and that's also P. So maybe for this chapter it's better to write the word out so we don't confuse power and pressure. What's the SI units for power?
Watts.
Good. What are the subunits for a watt?
Joules per second.
Good. And then we moved on to the concept of intensity. What would be the symbol for intensity?
I.
That's a good symbol. That's a logical symbol, and the textbook does use that symbol sometimes. However, we're a little uncomfortable with that because we've also used I for current.
Right.
So there's another symbol they use sometimes instead of I. You know what the other symbol they use is? No. Not maybe it's not logical. They decided also to use S, capital S. So intensity could be sometimes called capital I, or actually in this chapter it's more common to call it capital S, I guess because there's an S in the word intensity. Okay, so either of these symbols are sometimes used. So what would be a formula that would take us between power and intensity?
Intensity equals power over area. So S equals power over area, I guess.
Good. That's right. That's just a definition that you learned from the other videos that you saw or from class. Good. So what are the SI units for intensity?
Watts over meters squared.
You can figure that out from the formula. Good. There's no special name for those units. Good. But notice I'm not going to write down any particular formula down here because the exact area you calculate depends on the situation and the problem. I gave you a problem where it made sense to think of a spherical area, but other problems might have a different area. Let's see, that problem that we did a second ago, I gave you a 100-watt source, like a 100-watt light bulb. How would you interpret in words? What does that mean?
It distributes 100 joules per second for every 1 second.
Good. I think people have better understanding if they use the word 1. So we can rewrite this as the subunits, and the number we can put down here is 1. So you're on the right track. This means in 1 second, the light bulb will emit 100 joules of what?
Energy.
Yeah, in 1 second, it'll emit 100 joules of energy. So how much would it emit in 3 seconds?
300 joules.
That's right, good. So the power doesn't tell us the energy, but it allows us to figure out the energy. Or putting it another way, in 3 seconds, we'd have to pay the power company for 300 joules of energy to use that light bulb. Now, what did we figure out was the intensity on the previous problem? 1 over pi?
Yeah.
Good. What would we approximate that as?
1 over 3.
What would that be as a decimal?
0.3.
So approximately, this is 0.3, and the units for this are
Watts per meter squared.
Let's try to do the same thing with the intensity that we did with the power. How would you interpret in words what this means?
Something 1 meter squared away will feel 0.3 watts of power.
Say that one more time.
Something 1 meter squared away will feel 0.3 watts of power.
That's a good start. You put the number 1 on the bottom. That's good. But you said it was 1 meter squared away. That doesn't really make sense because something would not be a square meter away. Square meters are not the measure for distance. So actually, and after all, we were focusing on 5 meters away, not 1 square meter away. So that wasn't quite the right interpretation. What concept is measured in square meters?
Area.
Area. So that's how we should be interpreting it. So what you should be saying is, if I put a 1 square meter solar panel here, well, what can you tell me about this 1 square meter solar panel?
It'll feel 0.3 watts of power.
That's right. It'll be absorbing 0.3 watts of power. So notice, this number does not refer to how far away we are from the source. It refers to how big, I don't know how to put this word, but how big this thing is over here. After all, how far were we away? What was this distance?
5.
Yeah. So we don't want to confuse those different numbers. Okay, so now we have an interpretation for what intensity tells us. It says that if there was a 1 square meter object 5 meters away, it would be feeling a power of 0.3 watts. That means that if I hooked this solar panel up to a light bulb, it could only run a 0.3 watt light bulb. So not much power there. On the other hand, what if I made it bigger? What if I put a 2 square meter solar panel there?
Then you would have 0.6 watts of power.
That's right. So obviously this is common sense. If someone is trying to use solar power for their house, they don't put a tiny little solar panel out. They put great big solar panels because the bigger the area, the more power they're going to be able to get from that. All the solar panels will feel the same intensity, but the bigger the area, the greater the power you're going to get. Okay. Let's try this problem.
So, you know the intensity is, is 30 watts per meter squared. And you know it's going to circular disk with radius 2m. That means the surface area of this disk is 4 pi, which is like 12. And you know, I is power over area. So 30 equals power over 12. So power equals 30 over 12, which is 10 to the 4, which is 5 over 2 watts.
Okay, you have made an approximation, but that's good. All right, good. All right, that's a good answer. Excellent. So notice, so you just have to realize that you can solve this for the various things that you need. And this is very practical because, again, this is the kind of calculation, say, that someone who's designing a solar panel would have to figure out whether this solar panel is big enough to deliver the power that we need. Okay, good. What can you do with it?
I did it wrong.
Did you make a mistake?
Yeah. Sorry.
Oh, yeah.
It should be
Good thing you
30
checked.
times 12. Okay, let's see this bigger.
You have to change the pen back, otherwise
Oh,
you'll get a
I do.
huge pen. Because the size of the pen is the same as the size of the eraser.
12 times 30, which is 360 watts.
Okay, better. Good. If that's not enough power, what can they do?
You can increase the area.
Good. You can increase the area of the panel to get more power. What's the other thing they could do?
Increase the intensity.
Yeah, of course that wouldn't be practical for a solar panel, but for if you had control the intensity, you could change the intensity. How is intensity psychologically perceived? If you increase the intensity of light, how is that perceived?
It's brighter.
It's brighter. So this is why it's better to have a solar panel in the desert than in some place that's cloudy all the time, because you're getting a greater intensity. All right. One thing I just wanted to emphasize here is notice now we used a different formula for area. We did an earlier problem where you had to use the formula for the surface area of a sphere. But by looking at this problem, you saw that the area that you needed was the area of a circular disk. So you just have to be careful to use the correct formula for area at each point. Okay. So, how would you draw an electromagnetic wave? Well, it's not that easy because so many things are happening at the same time. But one thing you could do is, we need to have an oscillating electric field, right? So we can say, let's say the electric field is oscillating like this, up and down the page. So notice it's hard to draw because sometimes the electric field will be up, and then it'll be less up, then less up, then it'll be down, then more down, then more down, and then it'll start going back in the other direction. Any particular picture would just be a snapshot. So this is summarizing that the electric field is oscillating from all the way up to all the way down, back to all the way up again. So there must also be a magnetic field. How would the magnetic field be oscillating for this case? That's the key. Yeah, the key thing I want to go over is the electric and magnetic fields are always perpendicular to each other. So for example, what would be one way that the magnetic field could oscillate here?
Out and in.
Yeah, it could oscillate out to and into the board. Good. But I'm not going to make that decision because I can't draw that. So what's another way the magnetic field could oscillate?
Back and forth.
Left and right. Yeah, left and right. So I'll take that decision because I can draw that. So we can draw this to show the magnetic field. Now, this we're not saying that it's both directions simultaneously. It oscillates from all the way to the right to all the way to the left, back to all the way to the right. Now, so notice that there's two different directions we've talked about. We've talked about the direction the electric field is oscillating, which is up-down. And we've talked about the direction that the magnetic field is oscillating, which is
left, right.
In this case. But there's one more direction for the light, which is the direction the light wave is moving, right? For example, a light bulb, the light moves from the light bulb to your book. Or from the sun, the light moves from the sun to the earth. So what direction could this light be moving?
In or out?
That's right. So it's good that you didn't say up or down or left or right. Do these arrows show which way the light is moving? No. They just show which way the electric fields are oscillating. The light itself moves perpendicular to both of them. So just like you said the magnetic field is perpendicular to the electric field, we need to know that the direction of movement is perpendicular to both the directions that the electric and magnetic fields are oscillating. So there's three things that are perpendicular to each other. The direction, so which way is the light moving? Well, the light here is either moving into the board or out of the board. The light here could be moving either into the board or out of the board because that's the last perpendicular direction. So one thing that confuses people is that there's three different types of movement here. There's two directions of oscillation, and then there's what we could call the direction of propagation. So those are useful terms here. Is this a direction of oscillation or propagation?
Oscillation.
And this?
Oscillation.
Yeah. So what's the direction of propagation? In this case?
In or out.
Yeah, we don't know which one, but it could be either into or out of the board. So the way the light is moving is called the direction of propagation of the light. And the way these fields are oscillating is their directions of oscillation. So we don't want to confuse those two different types of movement. It would be easy to think the light was moving this way, but it's not. So remember, electric field is a vector. So the electric field is oscillating from between up and down. And magnetic field is a vector. So the magnetic field is oscillating between right and left. What would be a good symbol for the direction, for the vector, for the direction of propagation?
Like a dot or an X.
Let's see, a dot or an X. We can use a different symbol than that. What's the vector we usually use?
Velocity.
Yeah, normally throughout the course we use velocity to show which way something is moving. So how do we show which way the light is moving? V again, except now it's the V of the light. So in this case we could say that V is either into the board or out of the board. We haven't said which one, but it could be either of those. So we could use these symbols. This shows the direction of B oscillation, this is the direction of E oscillation, and either of these is the direction of V. Only one, the V is not oscillating. It's either always out of the board or always into the board. This is not an oscillation, we just don't know which one. Maybe to make things simpler, I'll just make a decision and let's say suppose it's this. Okay. So notice V is the direction of propagation, and these are representing directions of oscillation. Okay, so that is one possible way that we can try to draw the electromagnetic wave. It's a little hard to draw, but that shows the various points. So one thing that often is tested is that all of these vectors are perpendicular to each other. Maybe I should just draw them as vectors here. Now let's look at another way to see this. This will be hard for me to draw. Alright, so we can't get away from 3 dimensions here, so I'm going to try to draw a 3-dimensional graph as best I can. Hey. So let's say this is how the electric field is oscillating. So all of the axes here are space. This could be horizontally in space, vertically in space, and into and out of the board in space. What do we usually call this axis?
X.
Yeah, so I'll call this X, and this one?
Y.
And this one?
Z.
All right. So how is the electric field oscillating here?
Up, down, along the y-axis.
Those are both good answers. It's oscillating up and down or in the positive and negative y directions. Notice that this is a snapshot of one point in time. At one point in time, the electric field here is pointing straight up, and the electric field here is pointing straight down, and the electric field here is pointing straight up. Okay, good. That's just a snapshot. If you waited half a period, what would the graph look like? If you waited half a period, now the electric field up here would instead be down here. If you waited half a period, the whole graph would have reversed. So how is the magnetic field oscillating?
Along the z-axis.
Good. Or
along the x.
Yeah, or along the x-axis. But I don't think I can draw it along the x-axis, so let's draw it along the z-axis. Even that's kind of tough. Let's see if I can do that. Hey. Terrible. Hideous. Hard to draw. Alright, so I'm trying to use shading here to show that this is actually poking out of the page, and this is poking into the page, and this is poking out of the page, and into the page, whereas this is in the plane of the page, and this is in the plane of the page. But, I think you probably see what I mean, but anyway, this would be a better picture of what I'm trying to draw, basically. Okay. So I'll label this as B. So how do we say the magnetic field is oscillating?
Into and out of the plane.
The board.
Or along the z-axis.
Yeah, into and out of the board along the z-axis. Good. Of course, this is only a snapshot, because half a cycle later, the magnetic field will be pointing into the page, and then it'll come back to out of the page. Okay, good. So this clearly shows how these are two waves, why we consider this an electromagnetic wave. So what would we call, what could be the direction of propagation here?
Along the x-axis?
Yes, good. How did you know? Well, which way, along which axis is E oscillating?
Y.
And along which axis is B oscillating?
Z.
So to be perpendicular, the only thing that's left for the other variable V is along the x-axis. However, we haven't quite said which way. We haven't said whether it's moving in the positive or the negative x-axis. That's something they like to ask on exams. I don't know if I covered that in the video or not. Do you know how to figure out the direction of propagation here?
You do like a right hand roll, right?
That's right, yes.
But I don't really remember like which.
Okay, that's fine. Let's go through that. And of course, you don't need to have it memorized. We'll just put it in your notes and you can put it in your cheat sheet for the test. So first thing you realize is, one thing that you did was good, is you didn't try to use one of the old right-hand rules. We've learned a bunch of right-hand rules for magnetism, but this is a whole new thing. This is a whole new right-hand rule because this is an electromagnetic wave. So this new right-hand rule, and like I said to you before, one thing that's frustrating here is your TA might use a different right-hand rule because there's many that work, but I'll just give you the one that I use in the videos. So your fingers point in the direction of E, the palm in the direction of B, and what's the last vector?
V.
Good. This is a right-hand rule where you keep all your fingers straight. Good. Still might not be obvious how to use that, so how would you use that here?
Okay, so it'd be pointing to the right.
Let's see, so how did you get that? So you pointed your fingers up?
Yes.
Mm-hmm.
Pointed it up.
Okay, good.
I mean, I guess, okay, so I focused on like this point right here.
Good.
And your E is up at that point, your B is out. So then your thumb would be to the right.
So you chose to focus on this point.
Yeah.
So then your fingers should be up like the electric field. The magnetic field is pointing out of the page at that point, and then your thumb would be in the positive X direction. So we got here that V should be in this direction.
Yes.
And one thing that you did that was good here is you specifically said, I have to choose a point. It's good that you chose a point, but what happens if you choose, say, this point? So let's try it again for that point. So you get the same answer. Good. Which has to be the case, because remember, this isn't oscillating. So you can choose any point you want. So for this point, the electric field would be down, the magnetic field is into the page, but the thumb is still on the positive x-axis. Okay, so you don't have to do it twice unless you want to check your work, but you do have to pick a point. What you wouldn't want to do is use this and this together. Okay. Okay, so this is a new right-hand rule, so you want to have that in your cheat sheet for the next exam. This is the right-hand rule. And remember, this is something I see some people use sometimes. This is not for any old problem with electric and magnetic fields. This is only when the electric and magnetic fields are in an electromagnetic wave. Actually, this could be a little bit more general than that, but the only way this is probably going to be tested is when they're in an electromagnetic wave. They have to be from the same source anyway. So this is for EM waves, is where we're going to use this. Okay. This is a pretty popular type of question on the tests where they actually draw you a picture like this, this type of graph, and then they ask you to find the direction of propagation. Good. So let's try one more time. Let's find the direction of propagation for this wave. Looked like you were using this point here.
Yeah.
So at this point, fingers point out of the page for electric field, palm points up, and then thumb would be in the negative x direction. Good. So by shifting these, we shifted the direction of propagation. Okay, so that's how we use that right hand rule. Good. How does this relate to the ideas we were talking about up here? So we talked before about what happens when you increase intensity. How is that psychologically perceived?
Brightness.
Brightness. But how would it affect the graph? If we increase the intensity, how would our graph change here?
The amplitudes increase?
Excellent. That's right. So that's a good term. So these waves would all simply have a greater amplitude than before. So for example, the magnetic field would shift from cresting here to cresting here, and this would have a bigger amplitude here. Well, it would make the graph pretty messy, but you can increase all the amplitudes. Good. So intensity is related to amplitude. An increased intensity increases the amplitude. Good. So how is amplitude psychologically perceived for light?
Brightness.
Brightness. Good. Good. Let's talk about that term for a second. Show me the distance that represents the amplitude on your graph.
From here to here.
Good. So is the amplitude from crest to trough?
No.
No. The amplitude is from crest to equilibrium, or from equilibrium to trough. Good. So that's another term that you might need. Good. What did we say light is? What is light?
Oscillating EM wave.
Yeah, what does the EM stand for?
Electromagnetic.
Yeah, so what's oscillating?
Electric fields and magnetic fields.
Yeah, so light is really oscillating electric and magnetic fields. Or we can say, for short, light is an electromagnetic wave. What about, say, X-rays? What are X-rays?
Those are also EM waves.
Excellent, that's right. That's not obvious, is it? But it turns out that even though they're not visible, X-rays are also electromagnetic waves, oscillating electric and magnetic fields. What are radio waves?
EM waves.
I kind of gave it away in the name. But yeah, so they're also EM waves. What are gamma rays?
EM waves.
Those are also EM waves. Ultraviolet light is also. So it's all part of a spectrum. I think there's a picture in your book of all the different parts of the spectrum. Yeah, okay, good. So if X-rays are EM waves and visible light is EM waves, what's the difference between them?
Their wavelength and frequency.
Good answer. Yeah, the difference is They have different wavelengths and frequencies. That's right. Do you know what the order of the colors is in the spectrum?
Yeah, rosy bit.
That's a good number to get. Yeah, what does that stand for?
So red, orange, yellow, green, blue, indigo, violet.
Good. What's the difference between red and violet?
Red has a higher wavelength and lower frequency.
Good. What's the symbol for wavelength?
Lambda.
And for frequency?
F.
Good. I think you're, yeah, good, F. So one thing you're remembering is that wavelength and frequency move in opposite directions.
Mm-hmm.
So you can't just say that red is high. It's high wavelength, but it's low frequency. If it's high wavelength, why did I put it on the left here? Well, I decided to graph frequency rather than wavelength. So how would you describe violet?
Low wavelength, high frequency.
Right. Do you know what this part of the spectrum is right here? Right next to the violet.
Like what is it?
Yeah, what's the name for this part of this spectrum that's very close to violet, but not visible anymore? It has a logical name. It's called ultraviolet.
Oh, right. And then it's X-ray, then gamma ray.
That sounds right. Good. So this portion here would be ultraviolet.
Right.
And if you go even further, it'll be X-ray and then gamma ray. That's right. So why is this a logical name?
Because it's ultraviolet.
What does the ultra mean? It means high, higher frequency. This is higher frequency than violet. And what's this spectrum called? This part of the spectrum?
Infrared.
That's right, and that's a logical name because, do you know what infra means?
No.
Oh no, I guess this is a prefix that isn't used that much, but infra means below,
Oh, okay.
just like ultra means above. I guess infra is not used as much as ultra. But it means below because this has a lower frequency than red. And then after infrared, I guess, is microwaves and then radio waves. Okay, all right, so it's good to know these are all part of a spectrum that differ in wavelength and frequency. So again, this is a pretty impressive discovery because there's nothing obvious about the idea that radio waves and X-rays and yellow light are the same type of thing, but it turns out they are all the same type of thing. One more thing, do you happen to know what the wavelength of red light is, or what the spectrum, what the wavelengths are for visible light?
Like 400 to 700?
Yeah, that's worth knowing. Good. So which is in red?
700.
So this is approximately 700 what?
Nanometers?
Yeah, so it's a small wavelength. This is why it took so long for us to figure out that this was a wave, because we can't see the wavelength. It's so small. And this then would be 400 nanometers approximately. So I've added a little bit of information to the graph. Figure something out now. What can you figure out about this electromagnetic wave?
What has like, it's magnetic, no, it's electric. wave is 500. No, I can't. Okay, its electric wave is 1,000 nanometers.
Well, let's be careful. Those numbers are on which axis?
The x.
Right, which is not the direction of oscillation for E or B. So they don't really tell you anything directly about how E and B are oscillating. This is the axis of propagation, right? What I was going for is you can figure out the wavelength from that.
Okay.
So what is the wavelength?
The wavelength?
Of this wave?
Um, 500 nanometers?
So use your pencil to point out to me from where to where would be a wavelength on that graph.
From here to here, so it's 1,000 nanometers.
Okay, good. So there was kind of a trap or a trick in here. So I think at first you were saying that this was one wavelength, but this is actually half a wavelength, right? From here to here is one wavelength. So what's a wavelength here? How long?
1,000 nanometers.
Right, 1,000 nanometers. The 500 is kind of a trick or a trap. Why did you think this was a wavelength? Because they're both at this equilibrium point, but they're still not equivalent because this is upward sloping and this is downward sloping. A wavelength is the distance between two equivalent points on the graph. Well, this point is not equivalent to here because they have different slopes. This point is equivalent to here. That would be a complete wavelength. Okay, so that's something to watch out for. Remember we saw earlier how you don't want to misinterpret amplitude. It's not from crest to trough, it's from crest to equilibrium. You don't want to misinterpret wavelength either. Wavelength is not from equilibrium to equilibrium. It's from equilibrium to the corresponding equilibrium. Okay, so that's something else you can figure out. This is pretty popular in exams to give people this type of graph and require them to figure out stuff like this. All right, now that we know this wavelength, what else could we figure out about this EM wave?
The frequency, you know, the speed.
That's right, so let's do that. Let's figure out the speed.
So the speed is the speed of light.
Excellent, because I told you it was an EM wave. Good.
So, okay, so do it here. So if you know that it's 1,000 nanometers and you want to find the F, and the formula is lambda equals C times F. I think that's right. And oh my gosh, I don't know if this is this the right formula?
So
I'm forgetting everything.
turns out that this is the formula. You can just put that on your cheat sheet. So it turns out that this is the formula.
Okay. This is so sad. Oh yeah, okay, V equals F times lambda. So, and you know V equals C, speed of light, which is 3 times 10 to the 8. Is that the right?
And the units would be?
Meters per second.
Okay, good. I think that number would be given to you on the test, but that's right, that is the correct speed.
Okay. So we're starting with frequency, so it's going to be 3 times 10 to the 8 meters per second times 1 over 1,000 nanometers. Which is 1,000 times 10 to the negative 9. So that's your frequency.
Okay, excellent. Good. That was a good process. What was your answer?
3 times 10 to the 14.
And you ended up using these units,
Yeah.
so it's good that you put in your units.
Or I guess hertz. You can use hertz.
That's good. I was going to ask you what the name of that unit is. That's good to know. Okay. Good. So here's the formula we want. But you saw that so this is true for any wave. This would be true for a water wave or a sound wave too. But for this case, we can use c, the speed of light, like you saw. What's the interesting thing about this number?
Speed of light.
Yeah.
Works for all EM waves.
Yeah, just something about that. Is there anything important to notice about that number? Kind of a weird question. I just want to point out, we should take a moment to notice this is a very big number.
Oh, okay.
Does that make sense? Why?
Yeah.
Because it's the speed of light. So we should expect it so fast. Because notice, this is not miles per hour. This is meters in 1 second. In 1 second, the light has moved 3 times 10 to the 8th meters. Is that like, I think 300 million? 300 million meters in just 1 second. Okay, but that shouldn't surprise us because light is so fast, it seems instantaneous. When you turn on a light bulb, you don't see the light move from the bulb to the floor, but that's just because it's moving so fast. So this is something else, again, that's kind of impressive, that scientists can actually even measure this. Even though light is so fast, now we have a pretty good idea of actually how fast it is. Even though this is so fast, it still takes 8 minutes for light to get from the sun to the earth, because the sun is so far away. Okay, but on Earth, the light gets everywhere almost instantaneously. All right, so this is a number you need to use for any EM wave. They don't need to remind you of that on the test. You said that these units were per seconds or hertz. Oh, I was also going to say, I noticed that you wrote down all the units. That's fine since you didn't make any mistakes in your calculation, but it's perfectly okay since these are all SI units. To leave them out. Actually, once you do the unit conversion. So once you do the unit conversion, you can leave the units out. Although you got the right answer. And you did a good job with the scientific notation, because you won't be able to use a calculator. So this is the type of calculation you might have to do on the test with scientific notation. Good. What's another unit here for frequency? Instead of calling this per seconds, do you know what another unit is for frequency? Another subunits for hertz besides per seconds. Because per seconds is weird because there's nothing on top. Do you remember?
1 over S?
You could put the 1. What else can we put that's easier to interpret? What is happening here per second? These are...
Oh, like cycles?
That's what I was going for, yes. Actually, I think this is an important unit to know because this helps you to understand what frequency means. So notice part of this chapter is learning about EM waves, but part is just reviewing waves in general. This is so this is a place for them just to review waves in general from the first semester. So here's this concept. So frequency is cycles per second. So how would you interpret this number? What does this number tell us?
In 1 second, the wave completed 3 times 10 to the 14 cycles.
Yeah, cycles of what? That means that, for example, the magnetic field went from here to here and back to here 3 times 10 to the 14th times in just 1 second. So this is a very high frequency. Is this visible light?
No.
Yeah, what part of the spectrum is it in?
Infrared?
I think it's still probably in the infrared. Yeah, I think it's probably in the infrared. But even though it's not visible light, you can still do the same calculations here. So notice, even though this is called the speed of light, a better name would be speed of EM waves, because it works for any wave. Okay, so the thing here that's most likely to be tested is just this little thing that we did to find the wavelength. That actually comes up. You're likely to see a graph like this. So remember, here to here is 1 wavelength. Okay, good. So let's see if we can go back and build some more here. Remember I was saying if we increase the intensity, how is that reflected in the graph?
Increasing the amplitude.
Amplitude of what?
Of the wave.
Can you be more specific? What's oscillating in this wave?
Of the electric wave and the magnetic wave.
So the intensity is related to the amplitude of E and V. So we should be able to continue our flow chart here. This is a symbol that the book uses. You know what that symbol stands for?
No.
So the P here is just peak. So this is just the peak electric field. That's the same thing as the amplitude. So the book usually doesn't use the word amplitude. It says peak, but those are the same thing. Peak is the same thing as amplitude. So we should be able to relate the intensity of the wave to the peak electric field. I think that's a formula from the video, but there's no reason to have that memorized. Let's just write it down. So let's see. Let's see if I have it memorized. Okay, that's the formula. So we don't need to memorize that, but you should have that in your cheat sheet for the test. That's a fairly frequently tested formula for this chapter. Let me double check that I got that right. Let's see, this book is a little worse for it. S equals EP squared over 2 mu naught C. Excellent. All right. What does this stand for?
Intensity.
What do you think this bar is?
Average.
Yeah, so this is average intensity. And what does this symbol stand for?
The peak, the amplitude.
So notice that there's kind of a mix match here. We're relating the average intensity with the peak electric field. And those turn out to be what you're most likely to be tested on. The exams usually don't focus on average E, and they usually don't focus on peak S. What do we care about for practical purposes? So one thing that we didn't talk about, remember we did those problems about intensity before? But if you think about it, really the intensity should be changing constantly, right? The intensity would be constantly changing. What we were really doing was finding the average intensity and dealing with the average power. That's just taken for granted. So one thing I should say here is, if you see the word intensity in this class, does that mean peak or average?
Average.
You should just, that's just the assumption you should make. So anytime you see the word intensity in the homework or in the textbook or in the exam, you should interpret that as average intensity. And the same thing goes for power. So in this class, and in general, when people say intensity, if they don't specify, they mean average intensity. Like the problems I gave you at the start today, I didn't say average intensity, but that's what I meant. And that makes sense, because if you're building a solar panel, you don't care about how the intensity is varying each millisecond, you just care about the average intensity and the average power. Okay, so this is what we care about here. However, it turns out that we usually do focus on the peak of the electric and magnetic fields. All right. What's this symbol stand for?
Speed of light.
Which we were just talking about. You know that, but it'll be given to you on the test. And do you know what this is?
It's like that magnetic constant.
Yeah, it's the constant from magnetism. It's called the permeability of free space. I don't think you need to know that name. This is what we've seen before, is the numerical value in SI units is 4 pi times 10 to the negative 7. But you'll be given this on the test if you need it. I think this approximates to 10 to the negative 6, so you might be using that on the test. Okay, good. So what's the next thing we should be wondering here? Something I forgot to say. Notice one other thing that we forgot to say. We said that the electric and magnetic fields oscillate perpendicular to each other.
Yeah.
One thing I forgot to say, but I took it for granted here, is we also assume the electric and magnetic fields are in phase with each other. That's how EM waves work. So notice, for example, when the electric field is cresting, the magnetic field is not at equilibrium. That's just not how EM waves work. So when the E is cresting, the B should be cresting. And when the E is troughing, the B should be troughing. Actually, whether something's a crest or a trough is arbitrary. So when E is cresting or troughing, the other one should be cresting or troughing. And when B is troughing or cresting, the other one should be cresting or troughing. The key is you should never have one at equilibrium when the other one is cresting or troughing. All right, that's just a fact about EM waves that's built into the picture here. So anyway, coming back to here, we've seen that increasing S, we already said, remember, that increasing the intensity would change the amplitude. So now we can see how they're related. One thing you can see that you might not have realized is they're not proportional. S is proportional to the square of the amplitude, not to the actual amplitude. So if the EP increases, how is that psychologically perceived?
Brightness?
Yeah. Same as intensity. Because they move in the same direction, they're perceived the same way. Both intensity and peak electric field relate to brightness. How about peak magnetic field? That would also be brightness, because they're all related. I forgot to ask you, how is wavelength psychologically perceived? If you change the wavelength, how does that psychologically change the light?
Well, if you have a higher wavelength, then you're going to have a lower frequency.
That's a good start, but that's not psychological. How would that be psychologically perceived?
I think it'd be like...
For example, you said when intensity changes, the brightness changes. So what changes when you change the wavelength, psychologically?
Like what it looks like.
But we need to be more specific. For example, when you change the intensity, that changes how what the light looks like, because it changes how bright it is. Yeah. So when you change the wavelength, that doesn't change the brightness.
Well, I guess that would change its color then.
That's what I was going for. Yeah. So I just wanted to make sure you were familiar with the idea that intensity is psychologically perceived as brightness, but wavelength is perceived as color. We were already taking that for granted down here. We said that different wavelengths give you different colors. So wavelength is perceived as color. If I increased the size of these peaks, that would change the brightness of this light. But if I stretched out the wave along this axis, that would change the color. Okay. So how is wavelength psychologically perceived?
Change in color.
Good. How is frequency psychologically perceived?
Change in color.
Because you can't change the wavelength without changing the frequency. Because of this formula, since the speed of light is constant. By the way, notice this formula proves what you already said. High wavelength goes with low frequency. Mm-hmm. This formula proves that wavelength and frequency have to move in opposite directions because they're on the same side of the equation. All right, now going back up to our flow chart here, we shouldn't be quite satisfied because we haven't said how to find the peak magnetic field. So it turns out there's one more formula that you might use on the test, which is this. Mm-hmm. I'm not quite sure how to fit this into the flow chart to make it nice, because this is not just for peaks, this is for any point. So the electric field at t equals 0 seconds is C times the magnetic field at t equals 0 seconds. The electric field at t equals 5 seconds would be C times the magnetic field at t equals 5 seconds. The peak electric field would be C times
B peak.
Yeah, times the peak magnetic field. Average electric field would be C times the average magnetic field. So this is for any point in time. But we could build it into the flowchart here, because as a practical matter on the test is probably only going to focus on the peaks for E and B. The exam will probably only focus on the peaks. So what would be the formula that would relate these two? I guess I'll just write it like this to show this doesn't only work for the peaks, although this is where you're probably going to use it on the test. E equals CB. Okay, so now we have a larger flowchart here. We can move a bunch of different things together. Good. Does this mean that any electric field is C times any magnetic field? No.
For EM.
Yeah, remember this is only for these connected EB in the wave. Sometimes I see people just doing any old problem about electric and magnetic fields and they just kind of reach blindly for this formula from the cheat sheet. So we should make a note, this is only, in this class we're only going to use this for EM waves, not just for any old E and B that are not connected to each other. Okay. Notice that this also takes for granted that they're in phase, because when B is biggest, E will be biggest. Technically, I guess these are magnitudes. All right. So why don't we go back to that problem I gave you at the start? Do you have that? I guess we'll have to, it's in your notes. That was the first problem I gave you. A point source, here it is. Find intensity. Okay. So for that same problem now, let's also do this.
So we had that our intensity was 1 over pi watts per meter squared, and we want to find the P, so we want to find EP, and we know that the equation is S bar equals EP squared over 2C mu naught. So EP would be square root of 2C mu naught S bar, which is the square root of 2 times 3 times.
Good. That would be given to you on the test.
And then times 1 over pi.
Right, which we figured out from when we did the problem before. Good.
So the pi is going to cancel. So you get 24. 10. So
That's not so bad.
So okay. This is okay. That equals the square root of 240.
Okay.
And then you want to find the magnetic now, right?
Right.
Okay, and then this is the electric, right? So then what would the units be on this? It's a peak. Would it have units?
Yeah, you tell me. What do you think the units are?
It's a peak height. But it's electric field, right? Or electric field. So newtons per coulomb.
Ah, that's good that you remembered that. Yeah, good. So that's actually a good point that I hadn't been thinking about. Notice here the z-axis is not in meters. The z-axis is not in meters, it's in newtons per coulomb. Newtons per coulomb out of the board and then newtons per coulomb into the board. Okay, that's good that you know those units. Good.
And then now to find the magnetic, we use the equation E equals C B. So B would equal E over C, which is the square root of 240 over 3 times 10 to the 8 Teslas.
Okay, good.
Let's read the peak. Yeah.
Okay, good. You probably wouldn't have to simplify that on the test. You notice anything about this number? Your BP?
It's very small.
Good, so that's just a good thing to notice. So I just wanted to warn you, don't be scared if the B comes out small. That's just an artifact of the SI units. Because of the way the SI units happen to be defined, the magnetic field happens to be a lot smaller numerically than E. You can see that because it's getting multiplied by such a big number. The only since you're multiplying this by a big number to equal E, it must be a lot smaller. That doesn't mean we made a mistake. Okay, good. You might need to use those numbers in other parts of the problem. So maybe let's take another minute and simplify this a little. Do you know how to simplify that?
This one?
The 240, yes, root 240. Try working that out off to the side.
Well, that should be between
So you're trying to estimate what two integers it's between.
Okay.
That's a decent method. It's so big that it's a little hard to tell though. So I just wanted to review, since there's a square root here, the way you simplify a square root, what's a factor of 240?
24 times 10.
Now we don't know the square root of either of those, so we need to factor those some more. How could you factor one of those numbers?
4 times 6 times 10.
Good, now we're making progress, so.
2 root 60.
Good, let's try to factor this a little bit more.
3 times 2 times 10, which is 3 times 4 times 5, so 4 root 15.
3 times 2 times 10. And that's as far as you can go. Okay, good. So you don't have to do that, but if you're going to use this number later, it might help you to be able to simplify that. So that's the method for simplifying square roots. Just keep factoring. Good. So let's try plugging that in over here.
So
Okay, and there's not too much more simplification you can do, but let's rewrite this as a power of 10 in the numerator. So it's 4 root 15 over 3, or 4/3 root 15, but let's write the power of 10 in the numerator.
okay, so this is times 10 to the 0.
Good.
So times 10 to the 8.
Okay, good. If you had to use this number later in the problem, it might help to have this simplification. Okay, and this confirms what you said before, this is a very small number. Okay, good. All right, so those are some typical ways these types of ideas can get tested. Okay, let's try this.
So you know that power is 10 watts and you're 2 meters away. It's a point source, so your point source is going to have a spherical shape, so the area is 4 pi. R squared, so it's going to be 4 pi times 4, 16 pi. And you know your intensity is power over area, which is 10 over 16 pi. Which is 5/8 pi. And you're told to find the amplitude. And we know that, okay, so we know the amplitude of the magnetic wave, okay. And we know S bar equals EP squared. Over 2C mu naught. So, well, that's
Oh, we've done so much.
and I
so
write really big, that's why.
That's okay, but you can, there's infinite canvas here, so you can move to the side.
E.
Or actually, careful. Let's try to do this so I can send you the document. So,
I can just
let's try to finish this one over here, then we'll move someplace else.
I'll just write really slow. Well, and then, okay, I'll just do like this, 2 times, and this was, and then we know EP equals CB. So that means BP equals BP over C. So that means BP is going to equal this whole thing divided by 3 times 8.
Okay, good enough.
Yeah.
I'm satisfied. What's this one simple simplification you could make? Or is there a simplification? I thought there was.
Well, we can
Oh,
get
yeah.
rid of the tens.
Yeah, you could. Yeah, that's one thing you may as well do.
Okay. So you get, okay, well, alright, so you get, okay, 2 times 3 is 6, so 24 times 5/8 times pi squared times 10.
Alright.
All divided by 3 times 10 to the 8.
Alright, good. But where did you get this from?
Which one?
5/8 pi?
Right there.
Yeah, where did it come from?
Your S.
What was S?
Intensity.
Yeah, read it aloud. What numerical value did you get for that? Okay, yeah.
So, get rid of this. That's what I thought. I was expecting to cancel
Right.
out, and I was like, it didn't.
That was, alright, that's good enough. That was what I meant when I said the one simplification you might as well do is cancel the pi's.
Okay.
You may as well cancel the pi's. That's probably good enough.
Okay.
6, 24. Yeah, good enough. What are the units on that?
Teslas.
Alright.
So, T.
Okay, good. So this is pretty similar to what we did before. I just didn't give you all the hints. So in this one, you had to go all the way from power all the way to the other side of the flowchart. But it's still basically the same idea. And obviously, you could see a problem that moved you in the other direction in the flowchart too. There are a couple other formulas in the textbook in this chapter, but these are the only ones that are likely to show up on the test. So.
And I guess, did this chapter go over like energy and stuff yet or not yet?
It has some stuff on energy. That is very unlikely to come up on exams. There's some formulas that you can use for energy. You might need that. Mm-hmm.
We went over, okay, I don't even know if this was the same chapter though. If we did get over.
Well, in a way, we did go over energy. So, for example, for the problem that we just did, how would you find the energy? What would you need?
Your energy.
How does energy tie into this flowchart?
Well, your energy is your power times time.
So one way you could find the energy would just be power times time over there. There's also, there's some formulas for energy density that you might need for a homework problem. I have never seen those on an exam problem. For the exams, this is good enough. But if you need a formula for energy density, there's formulas in the book for finding energy density. So, we have a little more time left. So, let's see. I'll give you some new paper here. Yeah. Okay. Describe qualitatively how electric charges generate electromagnetic waves. Describe qualitatively how electric charges generate electromagnetic waves.
By accelerating? Like accelerating charges create those waves and then they like self-propagate.
Who's they?
The changing B and E fields.
Okay, good.
Self-propagate.
Good. So the key point is it starts with the accelerating charges. The key thing is that electromagnetic waves come from accelerating charges. Good. So that's a good start there. Oh, yeah. Let's try this problem.
Okay, so do we write on this?
Yeah, please.
Okay, so you know red light has a wavelength of like 700 nanometers. So you can find the frequency, I guess. So that's your frequency, and then your period is just 1 over your frequency, right? So your period would be 700 over 3 times 10 to the negative 17 seconds.
Okay, good. Yeah, you're right. That was the correct formula. So I just wanted to review that. Remember that we're just trying to review some also wave ideas because wave ideas can often be integrated with the material in this chapter. So that was a formula that we hadn't talked about before, but you remember that correctly. You can put it on your cheat sheet if you want. Period and frequency are reciprocals to each other. This would work for any wave, so it works for EM waves. What do you notice about this number?
Very small.
That makes sense. How would you interpret this number? What's that telling us?
That it only takes 700 divided by 3 times 10 to the negative 17 seconds to complete one cycle.
Yeah, one cycle of what?
Of like the wave. So from like trough, no, I don't know. But like to do that.
For who to do that?
For the EM wave.
What is it that's oscillating in the EM wave?
The magnetic and electric fields.
Good. Okay. Yeah, so you're on the right track. So what I was going for here is it takes only a tiny fraction of a second for the electric field to go from peak to trough and back to peak again. Mm-hmm. Or it takes only the same tiny fraction of a second for the magnetic field to go from peak to trough and back to peak. Or you could measure the period between those two equilibriums as well. It only takes that tiny fraction of a second to go from one equilibrium to the next corresponding equilibrium. Mm-hmm. Well, that makes sense because the frequency is so high. Because it's oscillating so quickly, it only takes a tiny fraction of a second. That's again why we can't see that light is a wave, because we can't see the oscillations. They're too fast for us to detect them. Okay, so I just wanted to add That one extra thing that might sometimes come up for those types of problems. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.